Okay, the 2017 mechanics question, here are the calculations for it. So derive v squared equals u squared plus 2as. If you look at page 50 in your tables, you'll see these three formula. They're the formulas for linear motion with constant acceleration. So we're going to use the first two to derive this one. So if we look at the first formula, v equals ut, u plus at, v equals u plus at. Now, we're going to square both sides. So if I square both sides, I get v squared equals u plus at all squared. Now, when you square that side, you should find, so square the first, multiply the two of them and double it. So u times at is uat, and then double it. And then square the last, I get a squared t squared. Now, I'm going to factorize out an a from here, and I'm also going to factorize out 2. Even though there's no 2 there, factorizing is the same as basically dividing. So if you factorize out 2, it's like dividing it by 2. So v squared equals u squared plus, so factorize out the 2a, so 2 divided by 2, and uat divided by a gives you ut. Factorize out one of these a's, but I'm also factorizing out a 2, so it's like, as we said, dividing it by 2 is the same as multiplying it by a half. And if you look, this is the same as this, so I can replace it with s, and that's that first part derived. Now the second part, the cord is 32 meters long. Henry has a mass of 60, so his mass is 60. And when the displacement is 16 meters, you have to calculate his velocity. So we're going to use this formula because we know all the data. We're looking for v. So his initial velocity is 0. The acceleration is the acceleration due to gravity. And his displacement is 16 meters, so v squared equals, so if you square that out, you get you get 313.6, and then v is the square root of that, which is 17.71 meters per second. Very important to put the unit down. And then there's a few questions then about Hooke's law and such. Hopefully you can understand them from the definitions in the exam scheme. We'll go on now to the elastic constant of the cord is 250 newtons per meter. Calculate the length of the cord, or calculate the length the cord would have if Henry was suspended at rest. So we're dealing with simple harmonics motion and Hooke's law here. So Hooke's law, which says the restoring force is proportional to the displacement. Hooke's law is k times s. Now, the force, if he was at rest, then the only force acting on him would be his weight. And his weight is his mass multiplied by the acceleration due to gravity. So we can say that if he's at rest, then his weight is equal to the force that the spring would be acting on him. Now, so the spring constant K, or the elastic constant, is 250. So his weight his mass is 60 and his weight is 9.8. The acceleration due to gravity, and the acceleration due to gravity is 250, and then s for his displacement. So that's the length of the cord. So working all that out, multiplying these two and taking the 250 across and dividing gives you 34.35 meters. Now the next part, at the end of his fall, Henry oscillates with simple harmonic motion. The maximum displacement from his rest position is 1.2 meters. Calculate his maximum acceleration as he oscillates and his periodic oscillation. Now, if you go to page 54 in your tables, you will find the formulas for a lot of this. So the formulas that we'd be working on here, you have A equals minus omega squared times S, where omega squared is a constant. It's to do with simple harmonic motion. The period will be 2 pi over omega. And also as well, where are we getting this omega squared? Well, it's just a constant of the spring. So if we look at it, if you had if mass times acceleration, or sorry, even before I do that, the force is minus k times s. Now, and in this case, the force is his weight, so mass times acceleration, that's weight, equals minus k times s. So that will give you then, if you take the m over cross and divide, so linking these two equations together, then that gives you omega squared is k over m. So I hope that's kind of clear. So if we start substituting in the relevant values now, then his acceleration will be 250, which is the spring constant k. So if we just look at this, the acceleration is the spring constant k over his mass, which is 60, and then times his displacement. So his displacement is 1.2, and sorry, that's negative. So if we multiply all that out, we get his acceleration is minus 5.00 meters per second squared, and that's as it should be, because the acceleration is always opposite to his direction of motion, because it's a restoring force. It's trying to get him back to the equilibrium position. And then the last part, the period of his oscillation. So using the formula that we listed up there, 2 pi over omega. So remember that if we just do an aside here, omega is 250 over 60. Sorry, omega squared is 250 over 60, which that's roughly 4.17. So therefore, omega will be the square root of 4.17. So the period then is just 2 pi over root 4.17, and that will give you 3.08 seconds.